Thank you very much, Sasha. It's a pleasure and honor to speak at the seminar in Chicago. I'm grateful to Sasha for inviting me, and it's my first time. I'll we'll be talking about 3 topics in one talk, even though the 3 topics that Sasha mentioned were 3 different talks. Usually it's a bad taste to have more than one idea in one talk, so it will be basically one idea with 3 different views of this idea. This idea will be useful for both decoding and testing that I will define, and then it will be just very natural to show an application of this idea to something nice like PCPs. This is joint work with Russell Impaglazzo, Rajesh Jaiswal, and Avi Vigdushan. Actually, it's based on 2 joint works, 2 papers, one on decoding and the second one on testing and PCPs. So I'll be talking about direct products, and the original motivation, as far as I understand, of direct products came from the problem of amplifying computational hardness of problems or functions. Here you have a function which is somewhat hard on average, so it's any algorithm of bounded resources can compute the function on all but at most delta fraction of inputs, and you want from this somewhat hard function to get a much harder function, which is hard almost everywhere, so every algorithm makes mistakes on almost all inputs. And one natural way to do this, to get from F to G, is by direct product. But here's a more formal definition of what I mean by hardness on average. So on the left, you have a function f, which you assume is easy everywhere except on delta fraction of inputs. And it's easy with respect to, say, algorithms which are circuits of size s. And so the definition is that delta hard with respect to size s if every circuit of that size fails to compute on at least delta fraction of inputs, the function.
The function is not 0, 1
in this case, it is Boolean, but our results will apply to general, not necessarily Boolean functions.
And I'm a little bit lost. Why delta is more than 1/2 or less than 1/2?
Yeah, so for Boolean, delta will be less than 1/2.
More than 1/2.
Well, delta is where it's hard to compute. So if the function is Boolean, then you can always compute it on a half.
Output constant.
Right.
Everything
is easier on a half. Yeah. So delta will have to be, delta is the hard part, so it should be less than a half.
No. So you are saying 1/2 plus delta.
Anyway.
So delta where you make mistakes. So you make mistakes on at most 1/2 of the inputs. Anyway. So the easy part will be at least of size 1/2. The hard part will be of size at most 1/2. No? Okay. So you do amplification by repetition. The intuition is that if you have hard time computing function f on a given single instance x, so that on a random axis is difficult to compute with probability 1 minus delta, then if you take k independent random inputs x1 through xk, intuitively the best you can do is to compute function individual on each one of them. And if each one succeeds with probability at most 1 minus delta, by our assumption, then intuitively you will succeed on all k of them with probability at most 1 minus delta to the power k, which is some exponential in negative delta k fraction of inputs. So that's the intuition. This intuition turns out to be correct for circuits, and I will talk a little bit more about this just later. For now, I want to define more formally direct product function. It's just Cartesian product of a given function from domain U to range R. Its k-wise direct product is a function which takes a k-tuple of inputs and outputs a k-tuple of outputs, where it outputs the value of f on the corresponding element of the k-tuple of inputs. So direct product theorem says basically that if function f is somewhat hard, then its direct product encoding is much, much harder. That's the formal way of stating the intuition that I had on the previous slide, where the dependence of new hardness on the previous hardness is this exponential dependence that you would intuitively expect. Okay, you go from 1 minus delta to 1 minus delta to the power k, roughly. Okay, so this is the picture. Here you had some small but not negligible hard part. Here, almost everything is hard.
What is epsilon now?
So epsilon now is this exponential in negative delta k. So you start from delta hardness and you get to 1 minus epsilon hardness, where epsilon is exponential in e to the negative delta k. So the easy part shrinks exponentially fast. And the new function is non-Boolean, by the way. So even if f was Boolean function, the new function outputs k-bit strings. So one can view the direct product function as a sort of an error-correcting code. And this was noticed in papers by Paglazzo and Trevisan, and actually can be traced to even earlier papers by Alon, Brucknauer, Nauer, and Roth, and later work by Guruswamy and Indyk used something like this construction. So you take a bipartite graph where the nodes on the left are labeled by the elements of your universe, and the nodes on the right are labeled by k-tuples of the elements of your universe U. You think of your function f, the truth table of your function f, as the message with each bit labeling the corresponding node on the left. And then the encoding would be the labeling of the nodes on the right, which you obtain by simply taking a node here and concatenating together the values of the function on the neighbors of that node on the left. Okay. So this is a particular construction where your bipartite graph is basically complete from the right-hand side. So every node here has degree k. And this corresponds to the case where you use all possible k-tuples to encode your function f, your message function f. Okay. So this is, there may be also a kind of de-randomized way of encoding the function f, where instead of using all possible k-tuples here, you pick some carefully chosen small subset, some pseudo-random subset of k-tuples, and only look at those nodes in this bipartite graph, and look and use their encodings as your code word of the message f.
Just a minute, how is that graph constructed?
So the graph is, every node here you have like u to the k nodes on the right. Each node corresponds to k-tuple of nodes on the left.
Yeah, but which k?
Which k doesn't matter.
How does it matter?
What are the H's?
Huh?
What are the H's?
Yeah.
What are the H's?
So, okay, I label each node here, I label by some string. Okay, and this string tells me which node to connect it to. So each node here is labeled by k-tuple of elements from U.
Regardless of how it is.
It's all of them, right? So every k-tuple will appear on the right, and this k-tuple will correspond to a node which is connected to the k elements.
Where the things are one, right? No.
Disregarding the order, right?
Disregarding the order. So I'm not saying anything particularly clever here. I'm just saying the direct product function can be viewed in this graph theoretic form by simply saying, okay, I have the value of the function f on all the k-tuples. It's as if for a given k-tuple, the value of the function on this k-tuple is just, I look at the position, this, that is first element in my k-tuple, this position, second element on my k-tuple, and so on, take the value of the function on those tuples and concatenate them together. And this will give me a string here.
Sounds right. You should have some structure on the edges. You should know which arguments go where formally. I don't know if it is important, but formally he's right. It should be a label graph.
Anyway, I think as we go ahead,
So the vertices on the left are labeled by elements from U.
No, edges could be labeled by the coordinate.
But numbers 1 through k.
Yeah, one numbers 1 through k, yes.
So it
Yeah.
formally right. I don't know if it is important or not, but formally.
Okay, it actually won't be important at all because I won't be talking about k-tuples, but I will be talking about k-sets in the rest of my talk. Okay, so hopefully we will agree that this describes some kind of encoding of the function f. Recall that I have the bits of the function labeling the nodes on the left, and then the k-tuples, k-bit strings labeling the nodes on the right is my code word of this function f. And what are the parameters of this encoding, if you want to call it a code? Well, the good things are that the encoding is local in the sense that if you give me this node that you want to know the value of the code word at this position, then I can easily compute it by just evaluating the function on the corresponding k neighbors of this node. So I just need k evaluation of the function f. K will be small usually. The function f, if it's easy to compute, then it will be easy to compute the corresponding coordinate in the code word. So it's locally, I can locally encode for each position in the code word. I can find the value of the code word there. And it depends on only few bits in the message. There will be also local decoding algorithm for this code, which means that if you give me a corrupted code word, if you give me code word which some positions have been wrong, then I can reconstruct the original function f locally also, in the sense that if you give me the position that you're interested in, then I can locally, by querying only a few positions in the corrupted code word, recover the value of the function at that place. Okay, so local encoding, local decoding. I have to say it's local approximate decoding, and that's unavoidable. Approximate decoding here means that I won't be able to recover the whole function f on all inputs, but I will recover a function f on all but some small delta fraction of inputs. Now, the bad things about this code, there are few. The distance of this code is poor. What does it mean? It means that if you start with two messages which are close together, their encodings will also be close together. Okay? So ideally, in a good code, you want two messages which are different in just one position to be spread far apart by the encoding. That's the definition of the code, usually. Okay, so the more the distance, the better the distance of the code, and you want codes with good distance. Here, we don't have code of good distance. Nonetheless, it's still good code to use for complexity theoretic purposes in the context of the direct product theorem that I mentioned. Another bad thing about this code is superpolynomial rate, which means that the length of the encoding is more than polynomial in the length of the message. Again, it's not something that you would like. Usually we would like the encoding to be linear or constant factor of the length of the message. Here it's much worse than that. However, you can still do something with this code. The poor distance issue can be treated by saying that you have some kind of distance amplification, in the sense that if you start with messages which are far away from each other, then they will be mapped to far away code words. Okay? And superpolynomial rate can be also treated by looking at so-called gerandomized direct product code that I alluded to in the previous slide, where instead of all the possible k-tuples, you look at a small subset of pseudorandom subset of k-tuples. Okay, this will be a smaller subset, so it will correspond to a smaller length code words. And in fact, you can get polynomial rate this way.
Yeah, but there you require some hardness result. You will be assuming some hardness result.
So for now, I'm not talking about hardness. Hardness will be byproduct of the properties of this code. Okay, so what does hardness mean? It means that if function f is somewhat hard, then its encoding is much, much harder. So the contrapositive of that would say, suppose I have an algorithm which computes the encoding slightly well, which means that it's correct on some small but non-negligible fraction of the positions. Then my decoding algorithm for this code will be able to recover the original function f algorithmically. So
I mean that de-randomization, that would be unconditional?
De-randomization is also unconditional. It's just about the code construction. Sorry, I didn't understand the question. Okay, so for direct product code, we have two basic questions, decoding and testing. So decoding means given something, given some Oracle C, which is approximately equal to the correct code word f to the k, where f are a message, find the message f. And the applications would be the hardness amplification. I was explaining it to Kiran just now that if hardness amplification is obvious if you have the decoding algorithm, because the decoding algorithm basically allows you to boost. If you have some algorithm which does reasonably well on f to the k, then you can decode and get an algorithm which does very well on f. Okay, so the decoding basically corresponds to amplifying easiness or hardness, depends on which direction you look. The testing is given a Oracle C, which may or may not be a direct product code or maybe arbitrary thing, arbitrary Oracle. You want to test if it is a direct product encoding of some message f. Okay? So you want to decode and you want to test if something is a code word. Basic questions. The second will have applications to PCPs that I hopefully will get to. So decoding versus testing, there are significant differences between the two, and it is a bit of an lucky coincidence that we are able to use same ideas to do both, because in general there is no real connection between the two, between decoding and testing. So what is the difference? In the decoding, you assume that C is corrupted code word. So you assume that there exists some f such that C is close enough to f to the k. This is your promise. And then you solve a search problem finding the message. And you want to do it locally, so you want to minimize the number of queries. But the queries will not be constant. In general, it will be some function of the parameters, like the distances and so on. In the testing question, you have no promise on C. C is an arbitrary oracle. You actually want to test if it is approximately equal to some f to the k. It's a decision problem. Yes, no answers. And in the testing case, you really want to minimize the queries to be constant, like 2 or 3 queries. Sasha?
Why you cannot use decoding algorithm for testing? Or you just run it?
Because here, the number of queries will not be constant, usually, in the decoding. It will be some function.
Right?
What?
The promise part is irrelevant for this, because I don't care if it doesn't fulfill my promise and does something ridiculous, then it's okay.
Yeah, that's true. So what I try to say in this slide is that there is no formal connection between the two tasks.
But only because of the number of queries. The first.
That's a big only if.
Are not relevant for this remark. That's what I'm saying.
Right. Right. So the number of queries is actually a crucial point. So you want to go to constant number of queries, which is something that you don't expect to do in the decoding case. So let me talk about the decoding first. So the decoding is actually, some kind of decoding has been known for a long time because that's a natural way to prove the direct product theorem. You prove it by constructive method. So the contrapositive of the direct product theorem, as I was already saying earlier, is you give an algorithm, ignore what size of the algorithm is, which computes f to the k with some exponentially small but not too small probability. Okay, so it agrees with f to the k on exponentially negative delta k fraction of inputs. Here's the picture. And you want to construct from that a circuit which computes function f on all but delta fraction of inputs. Okay, so it's kind of decoding. Yes, and this theorem has been proved many times. At first was stated in a paper by Yao, then first published proof appeared in a paper by Levin a few years later, and then there were different other proofs because this lemma has application in different settings, and some of those settings require different properties of the theorem, so they came with different proofs. And here today we'll see yet another proof, which is nicer than the previous ones. Otherwise, I would not tell it to you. So first, let me tell you what to expect in the decoding algorithm. First of all, you cannot really get unique decoding. So to decode from agreement epsilon, so agreement epsilon means that you start with an oracle which agrees with your f to the k on epsilon fraction of inputs. Epsilon can be very small, remember. But that's not important for this theorem. theorem says that if you want to decode from agreement epsilon, you need to allow not just one algorithm to be output, but a list of algorithms. And the number of this algorithm should be about 1 over epsilon. Why? Well, it's very easy. I can pick 1 over epsilon functions, which are completely different functions, and then define an oracle such that, I split the inputs into blocks of size epsilon, and on the ith block, my oracle agrees with the ith function on my list. Okay, so this oracle agrees on the epsilon fraction of inputs with each one of those 1 over epsilon functions. So if I give you such an oracle, and I'm interested in this function, f1, you have no idea that this is the function I'm interested in, so the best you can do is give me the list of all functions. And as this simple example shows, in the worst case, you can have at least 1 over epsilon such functions. So this is the lower bound on your list size. A priori, it's not clear that this is the right upper bound on your list size, that you cannot have more than 1 over epsilon. It turns out, as our result will show, that 1 over epsilon lower bound is tight. Okay, but it was not known before this work, as far as we know. I will not go into details of the previous proofs of the direct product theorem, because ours is nicer, but to give you an idea, it follows very natural intuition. So what is the intuition? You have a circuit C which does something non-trivial on k tuples of inputs. You're interested in particular input X. Obviously, you need to use this algorithm somehow. So given input X, you just randomly plant it into a random k tuple, run the circuit, and since you yourself chose those random neighbors of X in the k tuple, presumably you may know the correct values on those guys. And so you see the output you look at the output of the circuit and see how many things outside of your input X it got right. If it got many of them right, then intuitively you have more reason to believe that the circuit is correct also on your input of interest. Okay, the intuition is that somehow the circuit must say correct things in a correlated way. So the more correct answers you see outside, the more likely you believe the answer it gives on your randomly hidden input inside the k tuple. Okay, so that's the intuition, and this intuition has been made to work in a number of papers. What is bad about it? Well, to get this intuition implemented, you need to know the correct value of the function on those R1 through Rk that you randomly select yourself. Those are random things, so the way you solve it is by saying, okay, I'll need advice. I need to know the value of my function f on a bunch of randomly chosen inputs. And the number of these randomly chosen inputs that you would need for this algorithm to work is about polynomial in 1 over epsilon, like 1 over epsilon squared or something of that order. Okay, so this will be your advice, and if you want to get a list of algorithms, then this kind of approach will tell you, okay, enumerate all possible advice strings. Each one of them will give you values of the function on those randomly chosen RIs, and each one of those advice strings will give you one algorithm. If you have advice of size polynomial 1 over epsilon, the number of algorithms will be exponential in that, and that's what you get from the classical proof of the direct product theorem. Okay, so the advice is exponential. Our previous lower bound says the advice is at least 1 over epsilon. This upper bound gives you advice exponential in 1 over epsilon. Huge gap. In previous work with Russell and Ragesh, we were able to reduce this gap to polynomial 1 over epsilon, but this result has had many problems. First of all, it was complicated, it was recursive, and it was still suboptimal because it still worked only for a certain range of parameters. Okay, so today you'll see the better algorithm, which achieves the perfect list size 1 over epsilon, which is tight. It's relatively simple. I mean, it is simple. The analysis is also relatively simple, and it generalizes to give also a randomized version of the code. The nice thing about it is that no advice of the form input value of the function on the input is needed. Okay, so we don't use the approach that I showed on the previous slide when you want to know the value of the function f on a bunch of random inputs. Okay, no advice. So here's an algorithm. The algorithm is like this. You pick a random k-set. So here's where I make a transition from k-tuples to k-sets so that people don't get confused. I could work with k-tuples, but then I would have to do things like randomly permuting k-tuples and such things. It's much cleaner for me to just say that my inputs are k-sets, so no order. So I pick a random, absolutely random k-set of elements from my universe. Then I randomly partition it into two equal parts, A and B1, each of size k/2. And then I freeze these random choices. But these random choices will be made in such a preliminary stage. And once I fix these things, I will get my algorithm for any given input x. My algorithm will do the following. It will pass a random k-set through input x such that this random k-set contains my set A. It will run the circuit, my Oracle C, on this random k-set B2, check that the Oracle C answered consistently on the common part, and if the consistency was there, then we believe the answer of the Oracle C for the position x. Okay, so once again, given x, you pass a random k-set through that x, conditional on containing this common set of reference A, and see if your thing is consistent with respect to this reference set B1A. If it is consistent, you believe it, and output. If it's not consistent, then you sample another random B2. Okay, so take a random set through X again. So the first part can be viewed as pre-processing stage, where you pick this make this random choices and freeze them for the rest of the algorithm. And then with this random choices, the algorithm is randomly sampling sets containing this common subset A and checks for consistency, outputting the first answer that it finds consistent, else you're sampling set B2 for a small number of times, like 1 over epsilon log 1 over delta number of times.
So your advice will be only the choice of these things, AB1 or what?
Yeah, except that it's not really advice because I just randomly pick. My algorithm is randomized.
Yeah, no, but if you want.
Right, okay, so what can I prove about this? With probability about epsilon over the choice of the first thing, the random set and its partition, the algorithm that I obtain afterwards with this choice of the preprocessing stage will compute my function f on all but delta fraction of inputs. Okay, so this is a randomized algorithm. It does randomly here, and then it produces a circuit. And for epsilon fraction of the choices here, the circuit will be good for f. Now, to get the list from it, you just randomly sample a few times, 1 over epsilon times. With constant probability, you get a list which contains.
So you look at these pairs, but you don't care about the values, right?
Right.
Yeah.
So the proof ideas involves. So we have these sets which have common part A, as on the previous picture. Let's call this configurations flowers for the obvious reason, and we have.
I'm sorry.
Yes.
People call it sunflowers, and it's I mean this notation goes back at least 60 years or 50 years. So is there any difference between flower and sunflower?
So sunflower usually assumes that all
Yes.
pairs of sets have the same intersection.
You don't assume.
I don't assume anything like that.
That's the difference.
So yeah, I don't care. Maybe these guys have more than just intersection A, but in particular they intersect in A. Okay. So the flower will be determined by one petal of the flower and the partition of this petal into part A, which is the common core for the flower, and the rest is B. We'll have the core values, which are the value of the Oracle C on this reference petal BA. And then we have a notion of consistent petals. Consistent petals are those which contain those K sets containing A, such that the oracle on this petal agrees with the oracle on my reference petal on the common part of the two petals. Okay, so consistent petal is the one on which oracle agrees with my flower defining petal, BA. Is the definition clear? And so what we'll do is flower analysis. Now, this flower analysis allows us to conclude the following kind of structural result that says that suppose I have my oracle which has agreement epsilon with direct product encoding f to the k, then there will be many, like epsilon over 2 fraction of flowers determined by some reference petal S partitioned into A and B that are nice in the following sense. So niceness of a flower means that the core of the flower is correct in the sense that the oracle on the reference petal gives the correct values for the function f. And you have many consistent petals. Many here means, again, like epsilon fraction. Okay. Another property is that in a random nice flower, almost all consistent petals will be mostly correct. Okay, so imagine that this is a random nice flower. Then if I pick a random consistent petal, with very good probability, the value of the oracle on this petal will be the right values of the function. All of this needs to be proved, but the intuition is that consistency implies correctness. So if you're in a random nice flower, and if you're consistent, then most likely that you are correct. So the correctness of the decoding relies on proving these things, but rather than proving these things, let me tell you why these things are enough to analyze the algorithm. So the fact that there are many flowers means that preprocessing is likely to pick a nice flower. With probability epsilon over 4, we pick a flower which is nice because the density of nice flowers is epsilon over 4. So preprocessing will succeed with probability epsilon over 4. The fact that in a nice flower there are many consistent petals means that the algorithm likely does not time out. Remember what the algorithm does. It tries to find a consistent petal containing given input x. If there are many consistent petals in the flower, you're likely to succeed. The fact that almost all consistent petals are mostly correct allows us to say that the output of the algorithm is likely to be correct, because it will find a consistent petal and it will believe it. And by this, almost all consistent petals are correct. So its belief will be well-founded. So I have a proof outline of this result. The first part, the fact that there are many flowers which are nice, is proved by sort of simple averaging argument. So I will not do it. The second part, that in a random nice flower, that's the more interesting part, that in a random nice flower, consistency implies correctness, is more interesting. It's proved by symmetry. So let me just do a rough idea of this second case. So here I want to show that consistency implies correctness. The idea is take highly incorrect set S prime and show that it can't be consistent petal in a random nice flower. Okay, so this will be the symmetry. We'll change the order. So usually we define a flower by first choosing the reference petal for the flower, partitioning into A and B, and then choosing petals in this flower. Okay, now let's do it the other way around. Let's first pick the petal S prime, and then we'll pick a random nice flower for that petal. Okay, so by assumption, I pick a highly incorrect set S prime. The red dots here mean the inputs on which the oracle C differs from the function f. Okay, so C of S primes gives me some values for each one of those inputs, and on this red guys, it's wrong. Okay, so S prime contains lots of wrong values for my oracle. When I pick a random flower, I will pick a random partition of the set S prime as my core A. Because S prime has lots of bad elements, a standard sampling result will tell you that a random A will contain a significant fraction of those bad elements. Now, if I do the extension, random extension of this core to the reference petal, what can I say? By assumption, this reference petal must be correct for the oracle, meaning that the oracle on here, restricted to A, must be correct. That's the definition of nice flower. The flowers also must be the petals must be consistent. So the values of the oracle here and the values of the oracle here restricted to common part must agree. But these two things together mean that the oracle on S prime restricted to A is different from the value of the function on that core, which means that this cannot be a nice flower. The oracle is wrong on the core of the flower. Okay. So this basic symmetry argument shows that if you take a random nice flower, then highly incorrect sets are not likely to be consistent petals in this random flower. Okay, so now let me switch gears and talk about direct product testing. It's relevant because it will use the same ideas as on the previous topic, the decoding part. But before I go there, so let me ask you if there are any questions about the algorithm. So I hope that you got at least the algorithm and agree that it's a very simple algorithm. And I essentially gave you the full analysis. I didn't do the averaging part, which is fairly simple. The main idea is this simple symmetry argument, and there are some technical sampling lemmas like Chernow bounds and such, which are under the rug there, but the rest is really just small technicalities. So fairly simple. So what is testing? I referred to testing earlier. So given some oracle, you want to test if the oracle is the direct product encoding of something. So the oracle just maps k tuples to k tuples. And you ask if there is some function f to the k, which is equal to the oracle. It's very easy to see the following. C is actually direct product encoding of some function f, if and only if you look at all pairs of intersecting k sets, S and S prime, with common part A, then the oracle agrees on the common part. If you think about it, given a table which assigns some values to tuples, how on earth can it be a direct product function? Well, if you look at two tuples in the table which have no common elements, the answers of the oracle on those disjoint tuples can be completely arbitrary and it will not contradict anything. The only information you get about it being or not being direct product is for tuples which have some intersection. Because presumably, on the same elements appearing in two tuples, the oracle must give the same answer if they came from the direct product function, from encoding of some function. Okay. So the only thing that you can get information from are tuples which have common intersection. Okay. And if consistency happens for all pairs of intersecting k sets, then it's very easy to see that there exists some unique function f such that c is equal to f to the k. Now, in the testing world, we don't want to test for all possible pairs of sets because it will be too many queries. So let's just assume that we'll make only one query. So we'll pick two random intersecting sets and check if the oracle is consistent on their common part. This will be our natural test. Okay? Random intersecting sets. So this is the picture. It should look familiar. We had something like that for the decoding part. And ideas for decoding are useful to analyze the testing part. I will give some intuition without going into proofs. More formally, the direct product testing is, given an oracle, make few, hopefully constant number of queries. If the oracle is honest to God direct product encoding, you must accept. And if the oracle is far away from any direct product encoding, you must reject. More precisely, quantitatively, you want this kind of guarantee that if the test accepts with probability epsilon, then the oracle actually is sufficiently close to some direct product encoding where the probability of closeness, the closeness measure is proportionate to epsilon. So we want to minimize the number of queries, hopefully make it 2 or 3. And the interesting case here is to analyze small epsilon. So epsilon is the probability that the test accepts. So small epsilon will correspond to some kind of list decoding regime. Okay, I will not talk more about this. But this is the interesting case to analyze. What is previously known? So first of all, this direct product testing business has been started by Goldrake and Safra in 2000. Their motivation for introducing this idea was to get a combinatorial proof of the Pcp theorem. Instead of doing some kind of low-degree testing, which is a standard way of proving PCP, they said, let's look at some kind of combinatorial analog that will allow us to get basically the same result as we can get from low-degree testing. And direct product testing was a natural thing to do. I hope to say a few more things when I get to the application to PCPs later in the talk. So they analyzed the case of the acceptance probability for the DP test, which was some large constant close to 1. The number of queries was constant but large. A few years later, Dinura and Reingold simplified their proof and minimized the number of queries to just 2. Basically, they analyzed the natural, this test here. And this will be the test that we'll also analyze in our work. So they also get that for constant acceptance probability, 2 queries work. They also showed that if you want to make the acceptance probability smaller and get your test to work for smaller acceptance probability, like inverse polynomial in K, for example, then you can do it as long as it's not too small. If it's 1 over K to the A for A less than 1, then it works. And if it becomes 1 over K or smaller, 2-query test does not work. Meaning that whatever it tells you doesn't have any relationship to the closeness of your thing to the direct product. Okay, so for very small, in particular for acceptance probability exponentially small in K, 2 queries is not enough. You need to have at least 3, maybe more. So what we show is that actually 3 is enough. So with just 1 extra query, we can analyze acceptance probabilities as small as exponential in negative square root of K, roughly. And also along the way, we get an alternative, much simpler proof of the result of Dunur-Goldenberg for the case of inverse polynomial with small acceptance probability and 2 queries. Moreover, we can de-randomize our tests in the sense that, as in direct product code, instead of all possible K-sets, you look at K-sets which come from some smaller pseudorandom set of K-sets. Actually, they will come from affine constant dimensional subspaces in some field. But I don't think I will have time to talk about that part. So the analysis of v-test. This is the v-test to remind you. Randomly pick 2 intersecting K-sets, except if they're consistent. Very simple. The analysis also involves some kind of structural result about flowers. The flowers we've just seen, same thing as before. And the kind of structural result you get in this setting of testing is the following. If your test accepts with reasonably large probability epsilon, then there will be many nice flowers where a nice flower will be such that there will exist a function g from the universe to the range such that for this particular flower, locally to this flower, this function is the direct product function for your oracle. So let me say it again. So there will be many nice flowers such that locally to that particular nice flower, your oracle is a direct product function. Okay. The way we prove it is by a notion of harmony, a harmonious flower. So if you remember, for the decoding case, I define niceness of the flower as saying that, oh, the oracle is correct on here, and then consistency implies correctness. Here, I cannot talk about oracle being correct on here because there is no notion of correctness here. I just have an arbitrary oracle. I want to test if it is equal to some direct product function f. It may or may not exist. So I can't work with correctness. The only thing I can work with is consistency. I can check if two things are consistent. Okay, so the notion of harmonious flower basically tells you that you can amplify consistency if you go to a random flower. Okay, what it says is there will be many harmonious flowers, such that in a harmonious flower there will be lots of petals, consistent petals as before. But more interestingly, on consistent petals, our test accepts with probability close to 1. Okay? So imagine that you now zoom in into a particular random flower, look at only consistent petals in this flower, pick 2 of them that are intersecting on something outside of the common core. Of course, they intersect in the core, but you pick 2 of them which have some common intersection E, then the probability that they will agree on this common intersection E will be close to 1. Okay, so what happened here, on the entire space, the test, the consistency test, had some possibly very small probability epsilon. Locally to a flower, this probability got almost to 1. Okay, so it has some kind of boost from small acceptance probability for v-test to a very large acceptance probability for v-test. The proof of this result works by symmetry arguments very similar to the decoding case, and I will not go into this at all. I'll just mention the main lemma. So if you look at harmonious flower with the assumption that on consistent petals, v-test, the consistency test accepts with probability close to 1, then you can define a direct product function for this particular local flower in a very natural way as the majority or the plurality function. Okay, given input x, you look at the consistent petals containing x and rule by the majority of the oracle on those petals containing x. And this majority function will be such that it's a direct product function relative to this particular flower. I will skip the proof, although it's a very simple proof by animation, but I don't think I'll have time for that. So let me again reiterate the differences between the differences and the similarities between decoding and testing in our approach. In both cases, we're saying that there are many nice flowers. The notion of niceness differed slightly in the 2 settings. Niceness in decoding means correct core, many consistent petals. Niceness in testing means many consistent petals, and consistent petals with intersection are very likely to be consistent on their common intersection. In both cases, we define exactly the same majority or plurality function. In the case of the decoding, this plurality function is the function that we want, is the decoding of the message. In the case of the testing, this function will be the direct product function for the oracle that we wanted to test if the oracle was a direct product function encoding or not. Okay. But as I said before, there is no formal connection between the 2 settings, and it was kind of a miracle that the same ideas and the same kind of flower analysis, ideas from the flower analysis worked in both setups, testing and decoding. The slogans for here was consistency implies correctness. Slogans for testing means that harmony implies that you're a direct product. If you're harmonious, then you're direct product. This was the case of two queries. And we know from the counterexample of Denur and Goldenberg that two queries do not allow you to test for direct product in the case of very small acceptance probability. So we need to do another query, and we do it by an extra third query. What happens here is this complicated picture. You basically have, from after the two-query test, you know that there will be many flowers. Each flower may have its own function, so that relative to this flower, Oracle has the direct product structure. Okay? But different flowers may have different functions G's associated with them that are direct product for each one of them, but there may be no global function G prime that will be direct product for many of them simultaneously. And this case can indeed happen, and this is basically what counterexample shows, that such a situation is possible for two queries only. So you need to make the third query to somehow argue that there will be a single function that is good for a bunch of those flowers. And this can be done without the third query if your acceptance probability is large enough. And if your probability is small enough, with just one extra query. So I'll just state the test. We call it the z-test because of the geometric shape. Basically, you take two sets with common intersection, check for consistency, and then you take another set with a common intersection and check for consistency. So you basically do v-tests glued together at the common set S2. Okay. And analysis would show you that this is sufficient to argue that if you pass a z-test with probability epsilon, where epsilon can be exponentially small, then you get the existence of a global direct product function G, which is good for epsilon fraction of tuples. I think I'm running out of time. How much time do I have?
How much do you need?
Half an hour? No. 10 minutes?
5.
5. Okay.
7.
7. Okay. So I would like to show you something about application to PCPs, which I think is a very nice application, although to be honest with you, when we did our work on direct product decoding and then testing, we didn't really have in mind this kind of application. It came out rather surprisingly as a very happy byproduct of our work. And let me tell you about this happy byproduct. It won't be technical. So I need to talk a little bit about PCPs. So I know that all people in this room have some idea about what PCP is. You don't actually need to know about PCPs because I will define the few little things that we actually need to understand the rest of the talk. I will be talking about so-called graph constraint satisfaction problems, which are defined. You think of your favorite problem like 3 coloring, for example. This is an example of a graph CSP. You have some undirected graph G. You have some alphabet which will label the nodes in the graph. And with each edge, you associate a constraint. Like in 3 coloring, it will be inequality constraint. And you want to know whether there exists an assignment of colors to the vertices of the graph that will satisfy all the edge constraints. OK. So the Pcp theorem can be stated as there exists some constant delta between 0 and 1 such that the two tasks, distinguishing between CSPs, graph CSPs which are satisfiable and those which are at least delta unsatisfiable, is NP-hard. Okay, so even if you say either it's satisfiable or it's at most delta or it's at least delta unsatisfiable, it's NP-hard. Delta unsatisfiable means the obvious thing that any assignment will violate at least delta fraction of edges, edge constraints. Okay. So the PCP proof is a very natural thing. The proof will give me an assignment of alphabet symbols to the vertices, assignment of colors to vertices. And the verifier will accept if f satisfies a random edge constraint. So my verifier will pick a random edge with endpoints q1 and q2 and query the PCP proof in those endpoints and check if the edge is happy. So this means 2 queries, and the soundness is 1 minus delta. So basically, the error probability is delta, the probability that you pick a bad edge. Completeness is perfect. So soundness 1 minus delta is constant less than 1, but we may want to make it much less, because this is like the probability of making a bad decision. We want to make the probability of bad decision as small as possible. The natural way which works is to do sequential repetition. Basically, given a proof f from V to E, you ask, you pick random k edges and ask for the endpoints of each one of them and see that all of them are satisfied. That will work. It will make the soundness go from 1 minus delta to 1 minus delta to the k for the obvious reason. The bad thing is that the number of queries will be huge. Each edge contributes 2 queries, so it will be 2k queries total. One may try to do a parallel repetition style of soundness amplification where, well, you pick your k random edges, but then you take the endpoints of these edges and the other endpoints of the edges and group them into 1 query each and ask a parallel query to the proof. So the proof, presumably, given a k-tuple of vertices, will tell you the value, the colors of those vertices in a k-tuple. And if the proof, in the second case of parallel repetition, where you ask k queries, k-tuples as your single query, if the proof was honest direct product encoding of the original proof, then what you do here is basically the same as what you do in sequential repetition. Because 1 query has the same effect as asking k questions independently, sequentially. Okay, so that's why Goldreich and Safra had this kind of idea, intuition, an approach, suggestion for an approach of getting combinatorial proof of PCPs. In this case, it's kind of approach to get soundness down. You say, well, to get soundness down, it's sufficient for me to somehow take a PCP proof which maps k-tuples to k-tuples of colors, and somehow check with few queries that this PCP proof has the direct product structure. Once I verify that it has a direct product structure, I am in the same case setting as in sequential repetition, where I know that the soundness goes down exponentially fast with the number of repetitions. Okay? So that's the idea. If you start thinking about it, you realize that it's not as simple as it sounds, because given a proof, you want to run a DP test. Presumably, you want to make as few queries as possible. Ideally, you would like to keep the number of queries to 2, because you started with a 2-query PCP, which queried a single edge, and you want to remain with a 2-query PCP after you did the soundness amplification. Okay, it's important to keep number of queries 2 for hardness approximation results that will follow from this improved PCP result. Now, as we saw for the direct product test, 2 queries is the bare minimum to do any kind of testing whether your Oracle is direct product structure or not. Okay. So first of all, you need to make 2 queries just to verify in some sense that your Oracle is has direct product structure. And then afterwards, you want to make 2 parallel repetition kinds of queries on this corresponding 2 k-tuples. So if you add those things up, then it seems like you would need at least to use 4 queries if you want to follow this approach. Okay, first do the testing, and then do the actual parallel repetition queries. That's not the end of the problems. So first, this shows that you may need to have like 4 queries at least, not 2 that we're hoping for. Second thing is that what kind of guarantee will you get from your direct product testing? Well, you wish the following. This is the ideal statement, which is not true. You wish to say that if the direct product test accepts with probability epsilon, where you want to keep epsilon small, then f has perfect direct product structure. It's actually equal to some f to the k. No way it's true. Okay, the best you can hope for is that if your oracle is accepted with probability close to epsilon, then you have direct product structure or maybe epsilon fraction of k tuples. Okay, so your direct product structure, you have direct product structure on small part of your proof. Well, that may not be good enough because you only ensured that you direct product on a small part. So only a small part of your proof is direct product. But then you want to make those parallel queries. What is the guarantee that you will fall into that small part which is guaranteed to have direct product structure if it's really small? Maybe all your queries will fall outside where you have no guarantee about direct product structure at all. So it's complete nonsense. Okay? So even if you have some kind of direct product testing, which is good, it doesn't necessarily translate easily into the PCP kind of soundness amplification reduction that we're hoping for. Okay. So we get a solution which actually works, which does 2 queries and does get the soundness amplification. How many minutes do I have? -1. Oh, okay. So I'll skip the history, and I'll just give you the PCP construction. The PCP construction looks like this. So here's the PCP proof. The PCP proof takes as input a k tuple of edges and gives us the values for the endpoints of those edges. This is the structure of the Pcp Oracle that we want. The query that we make to the Oracle is the following. It's described in this picture. You pick 2 k tuples of edges conditioned on square root of k of them having common intersection, having common vertices. And then you just check that the oracle applied to this set of edges is consistent with the oracle applied to this set of edges for the common vertices here. This is your consistency test. And then the second thing you test is that all the edges that got assignment from the oracle are happy, they're satisfied. So let me jump to the conclusions. So we get decoding and testing for direct product code. We also get the randomized, which I didn't talk about because there was no time. The analysis of the v-test itself is kind of interesting, and because of the structure of the analysis of the v-test, we were able to get this 2-query PCP construction that I referred to. This kind of, that locally to a flower you direct product encoding for some function was crucial for the analysis of the PCP test that I didn't show formally. This can be viewed as kind of parallel k repetition for restricted classes of games. So this is kind of an alternative to the famous Raz's parallel repetition theorem, which analyzes general games. And if you do repetition on general games, he shows that the soundness decreases exponentially fast. This is a different approach to prove something similar for restricted games, for those CSP, graph CSPs that I mentioned. We got some other results that I won't talk about. One thing I want to mention here, what we got is a parallel repetition in a style of Raz, original result. The size of the proof during the reduction increased as it increases in Raz's parallel repetition because your k tuples of queries are completely independent. You ask all possible k tuples of queries. So the randomized version is interesting because it would say that you can keep the size of the new PCP small, and yet you have good reduction in soundness. And that was proved in a beautiful paper by Moshkovitz and Raz a few years ago, and was somewhat simplified by Dinur Harsha a year ago. So recently, Dinur and Meyer used our direct product testing results and showed how to de-randomize them in the context of PCP. I mean, our testing result can be de-randomized. We showed it ourselves. But to use this de-randomization of the direct product testing in the context of PCPs was not clear to us. We couldn't do it. And so these guys came up with a beautiful idea that allowed them to push the PCP application of our testing result in the de-randomized case, getting closer to proving Moshkovitz and Ras result in a combinatorial way. Their proof is highly algebraic, uses polynomials, and so on. The proof that I showed you is combinatorial, just intersections of sets and so on. Their result is also combinatorial. So they almost get a full combinatorial proof of this result with some extra work needed to complete it. Now I stop. Thank you very much.
So does this, I mean, intuitively, does this give a common proof of that P equal to BPP, assuming what, and Pcp theorem? Is that the right way to think about it? Does it in some sense give a common
proof for?
I mean, this would give, your thing would simplify the proof of that P equal to BPP result, or not?
Which result? I don't understand.
That impermeable realism P equal to BPP, assuming, yeah. They also use hardness amplification in that proof, right? Assuming
So you're referring to P is equal to BPP assuming circuit lower bounds result.
This gives simpler proof or no?
This can be used to get the simpler proof.
Yes?
Yes, but there were other simple proofs known before. I mean, this result of impaglazo regression has been reproved a bunch of times also.
But I thought this is the simplest you were saying.
Our proof of the direct product result is possibly the simplest proof with analysis available, and it also gives you the right information theoretic bounds on the list size, so it's also uniform. So yes, we believe that our proof of the direct product is possibly the simplest, even without restriction. Our proof also works in the uniform setting, where we care about the list size, and we get the list size to be information theoretically optimal up to constant factor. Even with this restriction, our proof is still simpler than the previous one.
So there is that some uniform version of XOR lemma, so this gives something like that?
Yes, the uniform version of XOR's lemma was in the results that I said I will not show. Uniform version would be like Yao's XOR lemma.
Yeah.
So yes, we get Yao's XOR lemma here too. In the uniform setting. So the uniform setting would mean that you can go from agreement half plus epsilon to a list of size about 1 over epsilon square of algorithms such that one of them computes your function on all but delta fraction of inputs. And we do get that. We do get to the right list size from 1 half plus epsilon agreement to 1 over epsilon square list size uniformly. Previously, it was only known with the list size exponentially big in 1 over epsilon. Yeah, it's not immediate from our result, but with some small ideas, you get that.
Okay, thank you.
Thank you.